Symmetric versus asymmetric cryptographic algorithms. Cryptographic algorithms form the backbone of modern cybersecurity, enabling secure communication, authentication, and data integrity across digital platforms. These algorithms fall broadly into two categories: symmetric and asymmetric encryption. The choice between symmetric and asymmetric algorithms depends on factors like performance, scalability, and the nature of the data being protected. Understanding their distinctions is crucial for developers and system architects designing robust security solutions. Symmetric encryption, efficiency through shared secrets. Symmetric cryptographic algorithms use the same secret key for both encrypting and decrypting data. This approach ensures rapid processing speeds, making it ideal for scenarios requiring high throughput, such as real-time video streaming or bulk file transfers. One of the most widely used symmetric algorithms is the Advanced Encryption Standard, AES, which operates in modes like ECB, CBC, and GCM. AES supports key sizes of 128, 192, and 256 bits, providing varying levels of security depending on application requirements. Performance: symmetric algorithms typically require less computational power than their asymmetric counterparts, allowing them to handle large datasets efficiently. Use cases: commonly employed in databases, messaging apps, and disk encryption tools where speed is paramount. A potential limitation of symmetric encryption lies in the challenge of securely distributing and storing the shared key. If intercepted, the confidentiality of encrypted data is compromised entirely. To mitigate risks associated with key management, hybrid approaches combine symmetric encryption for data payload protection with asymmetric methods for secure key exchange. This strategy leverages the strengths of both paradigms effectively. Asymmetric encryption: overcoming key distribution challenges. Unlike symmetric algorithms, asymmetric cryptography utilizes a pair of mathematically linked keys, a public key for encryption and a private key for decryption. This design eliminates the need for pre-shared secrets, addressing one of the primary vulnerabilities in symmetric systems. RSA, Rivest-Shamir-Adleman, remains a foundational asymmetric algorithm, relying on prime factorization problems for security. Modern implementations often employ key lengths exceeding 2048 bits to counteract advances in factoring techniques. ECC, elliptic curve cryptography, offers equivalent security with smaller key sizes compared to RSA, reducing computational overhead. Its adoption has grown significantly in mobile environments where resources are constrained. Security: the mathematical complexity underlying public-private key relationships makes brute force attacks impractical against properly implemented algorithms. Authentication: digital signatures leverage asymmetric principles to verify message authenticity and prevent tampering. Despite offering superior security features, asymmetric algorithms generally perform slower than symmetric alternatives. For this reason, they're commonly reserved for tasks involving identity verification rather than bulk data encryption. Digital signatures: ensuring data integrity and authentication. Digital signature schemes extend the capabilities of asymmetric cryptography beyond mere encryption. By applying a sender's private key to a message hash, recipients can verify both origin and integrity using the corresponding public key. Common digital signature algorithms include SASA-PSS and ECDSA, elliptic curve digital signature algorithm. Both provide strong guarantees against forgery attempts while supporting various padding schemes for enhanced security. Signature validation involves recomputing the message hash with the received signed value. Any discrepancy indicates either transmission errors or deliberate modification of contents. These mechanisms enable secure software updates, email authentication, and blockchain transactions where verifying source authenticity is critical. Their implementation requires careful handling of cryptographic libraries and random number generators. Hash functions: building blocks of cryptographic security. Hash functions transform arbitrary length input messages into fixed-size outputs known as digests. While not technically encryption algorithms themselves, they play vital roles in authentication, checksum calculations, and password storage. Famous hash families include MD5, SHA-1, and the more recent SHA-2/SHA-3 series. Although MD5 and SHA-1 have been shown vulnerable to collision attacks, contemporary implementations favor SHA-256 or SHA-3 variants for stronger security assurance. Collision resistance, the ability to prevent distinct inputs producing identical hashes, is fundamental property of quality hash functions. However, even small changes to input result in completely different output values, making them useful for detecting alterations. In practice, cryptographic hashes support operations like password salting, adding random data prior to hashing, and HMAC construction, hash-based message authentication codes, for added security layers. Password storage, secure handling of user credentials. Proper password management relies heavily on cryptographic best practices. Storing plaintext passwords poses severe security risks, necessitating the use of salted hashes and dedicated password hashing algorithms. BCRYPT, SCRYPT, and Argon-2 represent state-of-the-art password storage solutions designed explicitly for this purpose. Unlike general-purpose hashes, they incorporate configurable work factors to resist brute force cracking attempts. Each iteration increases computation time required to derive a hash, making dictionary attacks exponentially more difficult. System administrators should periodically update minimum iterations based on hardware advancements. Multi-factor authentication complements these measures by adding additional verification steps independent of stored credentials. Combining cryptographic protections with behavioral analysis enhances overall account security. Transport layer security. TLS securing network communications. TLS protocols protect internet traffic through layered security mechanisms combining symmetric/asymmetric encryption, digital certificates, and handshake negotiations. It forms the basis of HTTPS connections widely used across online services. The TLS handshake establishes session parameters, negotiates cipher suites, and verifies server identities via X.509 certificates issued by Trusted Certificate Authorities, CAs. Clients may optionally authenticate servers using client-side certificates as well. Modern implementations prioritize forward secrecy through ephemeral Diffie-Hellman key exchanges. This ensures past sessions remain secure even if long-term private keys become exposed later. Support for modern cipher suites like ChaCha20 Poly 1305 provides efficient encryption suitable for diverse network conditions. Regular protocol upgrades address emerging threats and improve interoperability across devices. Post-quantum cryptography. Preparing for future threats. Advances in quantum computing pose significant challenges to existing cryptographic infrastructure. Quantum computers could theoretically break RSA and ECC using Shor's algorithm, necessitating development of quantum-resistant alternatives. NIST's post-quantum cryptography standardization project evaluates candidates capable of withstanding attacks from sufficiently powerful quantum machines. Lattice-based, code-based, and multivariate polynomial schemes show particular promise in this domain. Migrating legacy systems will likely involve gradual integration strategies rather than abrupt replacements. Developers should monitor ongoing research efforts and plan accordingly for future-proofing their applications. Hybrid crypto systems combining traditional and post-quantum algorithms offer transitional solutions until full transition becomes viable. Such architectures maintain backward compatibility while enhancing long-term security resilience. Blockchain technology. Cryptographic foundations of distributed ledgers. Blockchains leverage cryptographic primitives to achieve decentralization, immutability, and consensus among distributed participants. Each block contains a cryptographically secured reference to previous blocks, forming the immutable chain. Consensus algorithms like proof of work, POW, and proof of stake, POS, rely on cryptographic puzzles solved by network nodes. These mechanisms deter malicious actors attempting double spending or altering transaction records. Smart contracts execute predefined logic autonomously once deployed onto the blockchain platform. Their security critically depends on rigorous formal verification processes similar to those applied in traditional software engineering. Cryptographic hashing plays central roles in Merkle tree constructions, zero-knowledge proofs, and privacy-preserving techniques adopted by newer blockchain projects seeking improved fungibility and anonymity features. Cryptanalysis, breaking codes and strengthening defenses. Cryptanalytic research continuously tests the strength of cryptographic algorithms against known attack vectors. Successful exploitation reveals weaknesses that prompt revisions in recommended parameter choices or complete replacement with more resilient alternatives. Side-channel attacks exploit physical implementations rather than theoretical vulnerabilities in mathematical formulations. Timing analysis, power consumption monitoring, and electromagnetic radiation patterns can inadvertently expose secret keys. White box cryptography aims to protect implementations from such exposure by embedding keys directly into application binaries. However, this technique introduces trade-offs between usability and security effectiveness. Ongoing academic studies explore novel attack methodologies targeting various aspects, from elliptic curve discrete logarithm problems to lattice reduction techniques affecting certain post-quantum proposals. Vigilance remains essential amid evolving threat landscapes. Best practices for implementing cryptographic solutions. Secure coding guidelines emphasize minimizing direct manipulation of raw cryptographic primitives. Instead, utilizing well-vetted libraries reduces risk of implementation flaws that might otherwise compromise system integrity. Regular audits and penetration testing identify configuration missteps or outdated components, potentially exposing vulnerabilities. Automated scanning tools assist in identifying weak ciphers or insecure default settings. Key lifecycle management encompasses generation, storage, rotation, revocation, and destruction phases. Hardware security modules, HSMs, provide specialized facilities for protecting highly sensitive material. Education programs should equip developers with foundational knowledge about selected algorithms' inner workings alongside awareness of common pitfalls encountered during real-world deployment scenarios. Conclusion: this exploration of cryptographic algorithms highlights the nuanced interplay between symmetry and asymmetry in achieving secure communications. From classical ciphers to cutting-edge post-quantum proposals, each advancement builds upon prior foundations while adapting to new challenges. Developers must stay informed about latest developments in cryptographic science to implement effective defenses against ever-evolving cyber threats. Prioritizing education, adopting industry standards, and fostering continuous improvement will help safeguard digital ecosystems for years to come.